Week 7, Thursday. Today, I would like to continue on shearing stress for non-thin wall structure. Okay, so where we have done this problem on Tuesday, we have looked at the stresses at point A and point B. So if you look at on last Tuesday, where we finished off, we calculated the stresses. Okay, we determined the stresses at point A, point B. This is the expression for point B. And then we calculated the shear stresses at the centroid. Good thing, important thing to make you recall, at the centroid, either use the top section, bottom section. The answer is the same. Okay, so where I finished off last week, we were looking at the shear stress distribution equation, which I will do again because it was almost towards the end, but I will do it again. Okay, right. So we're going to continue on the shear stress distribution equation. But before I carry on, I like to talk about the rules. Okay, so remember I wrote we have written 5 rules. Okay, so rule number 1, right? Rule number 1, as you can see now, is V and I are what? Are constant. That is the rule number 1 that we have. All right. And then rule number 2 is the geometric centroid. Is the datum. Is the geometric datum. Then we have rule number 3 is the analysis starts from the distance furthest away from centroid. Rule number 4, the first moment of area cannot cross over the centroid. Okay. And rule number 5, you can only flow in one direction. Okay. So if this is our, so what we see, okay, this is our transformation over here. Okay. So this is X and this is our Y. And over here, as you all know, this is our cross section view. Okay, this is our cross section view. And if I would draw our transformation, this will be our Y, this will be our Z, this will be our rotation of our X. Okay. And we know over here we have our Vy. And if that is the direction of our Vy, right? If we look at the formula, so I've shown you why that we are looking for shear XY. So this will be equal to Vy over Izz, okay, Qz over T. Okay. So we know that over here, this is just a sketch. The horizontal line I'm drawing. This is our centroid. Okay, that's our centroid. And the thickness, okay, the thickness dependent on where, okay, dependent on where you're interested. This is the thickness, okay, depending on where you're interested, okay. This is the thickness, and dependent on where you are interested, this is also your thickness, okay. And if I were to draw a blue line across, okay, if I were to draw a blue line across, right, and this has a certain distance away from the centroid Y, right? It has a certain, this Y, where it stops, this line is also known as our constant shear stress. Okay, that is our constant shear stress line. Okay, so a key thing to take note is the thickness. Okay, so the thickness, what you see when it's non-thin wall. Okay, so this is a non-thin wall example. Thin wall is different. So the thickness is basically a geometry that is perpendicular to your vector Vy. Okay, so let's get that clear first. Okay, so just to recall the 5 rules. Okay, and then we are going to start writing the shear stress equation for the distributed the shear stress distribution equation. Okay, now so we're going to use this figure quite a bit. Okay, so I'm going to have this figure. As I said, I'm going to start this example or writing the equation of the distributed curve again. Okay, we start from the beginning. So this line is where our centroid is. Okay, and the distance, this distance, okay, is equal to 35 millimeters. That is our 35 millimeters line. So hold on, let me copy and paste this first. So we are going to write out, okay, we're going to derive the shear stress distribution equation. Okay, and we're going to derive the shear stress distribution equation. Now, by looking at the equation that I'm putting in box now, right? By putting in box now, we know Qx is always a variable. Okay. However, T can be a constant dependent on the section. Okay. So what do I mean by that? Okay, what do I mean by that? So if we were to focus on the flange, okay, so this is the flange. Okay, this is what I know as a flange. Okay, and if I were to section it this way, I'm going to draw a section line now. Right, where the red line, that's my section line now. Okay. So if the distance, okay, so we know the distance from here to here is 0. Or 15 millimeters. Okay, 15 millimeters. Okay, why? Because 35 minus 20 is 15 millimeters. Okay. So we're going to create what is known, as you all know in math, we're going to create a piece wise equation which is controlled by the constant thickness of the structure. Okay. So the first thing we're going to do, we're going to focus at the thickness is equal to 160 millimeters or 0.16 meters. Okay. So if you look at 160 millimeters thickness, constant thickness, okay, then the limits of our equation that we're going to write is between 0.015 meters and y, and the upper limit is 0.035 meters. Okay, so if now I were to draw my transformation, this is z and this is y, and where we are concerned now, if I'm going to sketch a blue line, okay, so that is the blue line is what we call our y. Okay, remember we are deriving the shear stress equation distribution, the shear stress distribution equation. Okay, so when that's the case, we are also made aware that there's a line over here. Okay, this line. Okay, if I zoom in, right, the top section and the bottom section are equal, and this value over here is known as our y bar. Okay, so from here we know that our Vy is a constant, Izz is a constant. So now we are going to write Qz as a function of y, and this is equal. So first moment of area about the zz axis. So if you ask me where's the zz axis, I will highlight for you. This is where we take our first moment of area from. Okay, so it's equal to A, or width, multiplied by depth, multiplied by y bar. Okay, so over here, this is our width, and over here, this direction, this is our depth. Okay, so the width for this case is a constant. So the width is 0.16 meters, right? Now the depth, right? The depth. So the depth thickness. So is this thickness over here. So if you ask me where is the depth, so this is the thickness over here. Okay, this is our depth. So the depth is equal to 0.035, and it's dependent on where on y. Okay, and then you have the y bar. Okay, so now there is the width and there's the depth, and then over here we're going to write our y bar. Our y bar is equal to 0.035 plus by y multiplied by 0.5. And why is that? Why is the y bar 0.035 plus y multiplied by half? If you look at the Tuesday notes, right, we did derive it. And when we derive it, hold on, this is not Tuesday's notes. If we look at Tuesday's notes, we did derive this, okay? So it's over here, as you can see, right, with this structure over here, right? The y bar is c plus y multiplied by 0.5. So c is the maximum distance away from the what? From the centroid of the point of interest, okay? So y is your variable, and then you just multiply by 0.5, okay? Exactly the same. So now, coming back to our question over here, or to our problem over here, that is how we calculate our y bar. Okay, so this will be equal to 0.035 squared times by 0.16 times by 0.5 is equal to 98 times